Okay, everybody, here is today's Zoom conference, October 3rd. This is what I thought we would talk about, depending on how many questions we have and how long it takes to do the other items. This could be only a 20, 30-minute conference. I'm going to talk about test 2 results and talk about some concepts that some missed, and then see if there are any questions. And then I'm going to give an overview of the functions we're going to be talking about. I say next unit, it's really the unit that we're talking about after test 2, which is function modeling. And then I'm going to talk about a great app for graphing something. If you're interested in graphing online very easily, I'm going to show you how to do it so you can graph some functions if you'd like to. A graphing calculator is not required. Now, test 2 results. This is a box plot. The grades went all the way from 56 to 100. The median was 82.8. The mean was 80.6. Basically, about 25% were below about 70. And I've invited anybody who wants to me to go over their tests with them. I'll be glad to do that. I've already done that with one person. But by and large, I talked to Dr. Andrews, who's the math chair, and he thought this was pretty much a good bit better than most of the other classes are doing. But I'm concerned about the ones that are not quite there, and I want to do all I can to help them. Now I want to talk about some things that were missed. One thing that stood out to me was the concept, not understood by some, was the understanding of the quartiles and their interpretation of the box plot. If you calculate the 5-number summary, I hope you understand that the first quartile is 25% of the people, or 25% of the data. And then the next quartile, there's 25%. And then the next quartile, Q3, that's 25% too. And then the next quartile is 25%. Now there were some questions on the test, like the middle %, and a number of students, although I would say the great majority got this one right, but the middle 50% were people who say scored, at least in this example, between 70.7 and 88.5. This is not the question that was on the test. It had to do with some other, something that was not grade related. But the top 25% were between 88, 85, and 100, etc. And so there were maybe 4 or 5 students that had a little problem interpreting this. Does anybody come in? Does anybody else come in?
Steven's here. I just showed up.
Okay, okay. We're not going to count you late. Okay. Stephen Parrish. Okay. One thing that caused some folks a problem was not understanding the sampling methods. There was a question in which one was stratified sampling and the other one was cluster sampling. If you break up the population into a bunch of groups and you only pick a few of them, that's cluster sampling. If you break up the population into a bunch of groups and you sample from each one of them, that's called stratified sampling. And if you go back and look at your test, it should be obvious what you may have missed there. If you have any questions, give me a call, email me, or text me or something. Another concept not completely understood was the data types. A phone number is not numerical, it's categorical. The number does not do anything with respect to any numbers as far as how big something is or how small something is. So it's a categorical. However, the birth year is numerical because the number in the birth year can lead to numerical information about the difference in you and somebody else's age, how old you are, etc. One of the other things I noticed, if you missed some of the answers in calculating like the 5-number summary, etc., you didn't check. One thing you got to do is double check your data. I would say do it twice. So you just did calculations and didn't get them correctly. So if it was that, if you were real close, you might have gotten some part credit. But in general, if you put the numbers in wrong and didn't check them, you missed it, just flat missed it. That's just like if you were in a job doing some accounting or something and didn't check your data, you're not going to do the company very well or do your boss very well or produce data that's good for the organization. So just check everything. So are there any questions? Are there any questions? Let's see. The only person that's come in is Stephen, other than Jennifer and Miranda. Okay, does anybody have any questions? Stephen, you got any?
No, sir, not this time.
What? What'd you say, Stephen?
I don't have one at this time, no, sir.
Okay, I'm going to require everybody to ask at least 10 questions. Does anybody else have a question? Jennifer? Miranda, I guess you don't have a question.
No, sir.
Okay, so you know all the answers. That's fine. One of the things I learned a long time ago, that if anybody thinks they have all the answers, they haven't heard all the questions. that made me sort of realize if I thought I knew everything, I may not have heard all the questions. Okay. Well, if we don't have any questions, I'm just going to go over some things that sort of summarize what's important in the third section. As you know, and these are some equations you can have on the next test. As you know, we're into linear functions. Is there anybody here? Everybody here has had linear functions before, right? Stephen and Jennifer. And
Yes, it's been a while, but I've done it.
okay. So this shouldn't be new. You may not remember everything. But,
yes, it was familiar when I went through the video.
Okay. One of the main things if you got 2 points, P and Q, and you have the coordinates, the slope of the line is just simply y2 minus y1 over x2 minus x1. Notice that that's the same as doing y1 minus y2 over x1 minus x2. As long as you do them in the same order, you'll get the same thing. You can't do y2 minus y1 over x1 minus x2 because that will be the negative of the slope. So if you'll just keep everything straight, you'll be able to calculate the slope. And then an equation you can have on the test, carry with you to the test, is an equation of the line itself, given that it passes through the point x1, y1 and has a slope m. It's just going to be y minus y1 equal m times x minus x1. And the other thing, y equal mx plus b, is probably the equation that most people remember for a straight line with a slope m and a y-intercept b. In other words, x equals 0, where x equals 0, that's the y-intercept, the b. And with this, you can do just about anything related to a linear function. Okay. And in the video, we worked a bunch of problems, given information, and just be careful, check your work. Now, has anybody watched the quadratic function yet?
I haven't.
Okay, do you remember quadratic functions?
Honestly, very little.
Okay.
Like I said, I haven't reviewed it yet, though.
Okay. What was the last time you had quadratics?
I graduated high school in 2013.
So that was 6 years ago. Okay.
Wow, that's right.
Absolutely. You know, if you're away from something for a while, unless you do something in it every year, you're not going to remember everything. It'll come back to you, I think. Jennifer, when's the last time you've had a quadratic? Jennifer?
I think my junior year of high school.
In high school, which was how long ago?
A year ago.
Huh?
A year ago, I just graduated.
Oh, a year ago. Okay. So you may remember a little more.
Yeah.
Okay. And I think there are some in the class that haven't done this in maybe 15 years. Okay. But a quadratic function is one that has x squared in it. And it can look different ways depending on A, B, and C. But one thing to remember, if this A is more than 0, it's going to go up like that. It may start here, it may be here, it could be here, could be here, could be here, depending on what A, B, and C are. But it always opens up if A is more than 0. That means that if it looks like that, it's going to have a minimum. And it won't have a maximum, it'll just keep on going up. As y gets bigger in that direction, x gets bigger. It just goes up very fast. Now, if A is less than 0, it looks like this, that, or that, or that, depending on A, B, and C. And it will always have a maximum. Okay? And you can calculate the maximum very easily. If A is 0, then there's no quadratic. There's no x squared term, and it's just linear. So it would not look like a parabola. That's pretty straightforward. So there'll be some problems for you to work next week as you get into the quadratic function. One of the things in my career that I worked on rockets and satellites. And this is a picture that I have of the space shuttle going into orbit. Obviously, you see a lot of smoke, but this was a mission I had on the space shuttle. And it's obviously a parabolic function. Now, the key things, and you need, I would have this with you on the test so that you can remember how to calculate various things. Here's just an example. A parabola will always have an axis of symmetry. That is, the x value equal some number that splits it right down the middle. It's called the axis of symmetry. And just remember it's a y equal ax squared plus bx plus c. To calculate that axis of symmetry, you just take minus b over 2a, and that gives you the x value. And then every quadratic has what we call a vertex. And that really is the point where it either has a minimum value or a maximum value. If A is more than 0, it'll have a minimum. If A is less than 0, it'll look like that, but that will still be the vertex. So I'm sure on the test, you're going to be asked to find the vertex by calculating minus b over 2a. And then to calculate the other variable in the vertex, h happens to be we call h minus b over 2a. And the corresponding y value is called k. And that would be the minimum or the maximum value So to calculate K, you just plug in the value of H. Now it turns out there's an alternate form of writing the quadratic equation. It's using the same A times X minus H squared, where H is equal to the minus B over 2A. And K happens to be the Y value of the vertex. So all you need to do to find the vertex is to calculate minus B over 2A, plug that X in to the function, and that gives you K. And so now you have that. Now I made sort of a mess here. The other thing, how many have heard of the quadratic equation? Quadratic formula. Stephen, have you heard of that?
Yes, sir.
Okay. Well, a lot of times you had to memorize it. I'm just saying you can have this on the test. It's probably one of the most famous formulas in the world, that for any quadratic function, this will give you the x-intercepts. That is where the parabola goes through the x-axis. So just plug in here and you got it. Now, let me just do some things. The parabola could look like that. And this could be x1, this could be x2, where it goes through 0. Or it could be turned over this way. And this could be, say, x3 and x4, where it goes through 0. And in these two particular cases, it has two separate real zeros. Now, what do you think would happen if the graph looked like this? Anybody got any ideas? Miranda, you got any ideas?
No, sir.
Okay, you're gonna learn it real quick then. Stephen, how about you?
I'm sorry, say it again.
So suppose it looked like this red parabola I just drew. Jennifer, what do you remember? Do you remember anything?
I remember, but I can't think of what it was.
Okay, obviously these two intersect the x-axis, right? But this one doesn't. This means there are no real zeros. Alternatively, if you had it looking like this, it never goes through the x-axis either, so no real zeros. How do you think you tell whether or not you have real zeros? Well, we do that with what we call the discriminant. Have you heard of that?
No, I don't remember the discriminant.
Well, you've seen this though, right?
Right. Yeah, I've seen them formally. Yeah.
Okay. Now, you know that whether or not you can calculate a real number depends on whether or not you can calculate the square root of b squared minus 4ac. If b squared minus 4ac is like 16, right? The square root of 16 is 4. So this number over here would be minus b plus or minus 4 over whatever 2a is. So you calculate a real number. But what happens, Miranda, if you got the square root of minus 16?
I don't know, -4.
What's that? No, it's not.
So it's,
You cannot come up with a real number when you square it, it's minus 16.
okay.
Would it, Jennifer, do you remember that that's 4i? Do you
Yes,
remember
sir.
that? Huh?
Yes, sir, I remember it.
Okay. Now I means it's imaginary number. Okay. So if b squared minus 4ac is less than 0, you've got the square root of minus 16 would be the square root of 16 times the square root of minus 1, which would be 4 times the square root of minus 1. The square root of minus 1, if you recall, is I, the imaginary number. Now, does that mean anything to anybody much? Well, what it really means is there are two complex conjugate roots. That could be like 3 minus I, and the other one would be 3 plus I. Now, to give you a little bit of relief, we're not going to have any complex roots in this course. At least we're not going to deal with complex roots right now. Okay. So all the equations you'll see will have either two real roots that are separate from each other. If b squared minus 4ac equals 0, there are two equal roots. In other words, if x is equal minus b plus or minus the square root of b squared minus 4ac is 0, then the roots are minus b over 2a and minus b over 2a. They're two equal roots. And that means that this parabola just touches the x-axis, either that way or this way. So don't worry about complex roots. Does anybody have any idea what a complex root might mean?
No, I can't remember that.
Okay. Well, I'll tell you the truth. Most people, most times I've seen quadratics taught, and they talk about complex roots. They just say, well, I is equal to the square root of minus 1, and that's all you're told. Turns out that if we had not introduced complex roots or imaginary numbers, then you would not have your cell phone, you would not have your computer, you would not be able to listen to anything on the radio or television, because the square root of minus 1 helps you understand radio waves. Has anybody seen the first video on functions?
Yes, sir.
You know, I think I talked about, it wasn't part of the required curriculum, but I thought I had to mention to you a sine wave, which carries information for satellites and for radio, and that's where all your data goes on. In other words, if we hadn't introduced imaginary numbers, we would be back in the dark ages. Okay, but that's something that's hardly ever mentioned to classes when they first talk about this. Only if you get into engineering is it mentioned. Otherwise, you'll probably never have any use for imaginary numbers. But that basically is quadratic functions. So what do you got to know? You got to know whether a is more than 0 or less than 0 to know which way it opens up or down. You need to know minus b over 2a is the axis of symmetry, and then plug that into the equation to get your y value of the vertex, and then use your quadratic formula to find the zeros or the x-intercepts. So that's quadratic functions. And then the next function, other than the linear function we've already covered, is going to be exponential growth. Now, have we already seen something about exponential growth?
Yeah, when we were talking about like loan payments and stuff like that, or and interest and stuff. You know,
like compound interest.
Yeah.
So this is not really going to be new. But when we talk about exponential growth, we're going to look at two ways to do it. Let's just do an example. Suppose you get 10% interest compounded yearly. So if you start with, I'm just going to use, say, A0 to start amount into the bank. Next year, you're going to have in the bank A1 is equal to A0 times 1.1. Everybody agree with that? And then A2 is going to be A1 times 1.1. So we can have a formula that says A sub n, like the nth year, is equal to the amount you had in the previous year, A sub n minus 1 times 1.1. So 1.1 is equal to 1 plus r, where r in this case was 0.1. So if something grows by r%, and then we write it as a decimal, little r, the amount that you have in the nth year is 1 plus r times what you had in the previous year. But then the explicit form, which you've already seen, is the amount you have in any time period is equal to what you had in the previous time period times 1 plus r to the n. R is the growth rate. And then 1 plus r is called the growth multiplier. Okay. suppose suppose things were growing at 35% growth rate. What would be your growth multiplier? Somebody tell me. What would be the growth multiplier if the growth rate was 35%? Jennifer, I bet you know. Nobody said anything. Is everybody gone?
No, I'm still here. I'm just trying to figure it out.
Wouldn't it be R?
Yeah, the growth rate is 35%. So little r is what, Jennifer?
It would be the multiplier.
Well, if the growth rate is 35%, what would r is 35%. So little r in decimal form would be what? You know, just like it's,
0.35.
huh?
Is it 0.35?
0.35. Okay, you got to get that down. Okay, it's just like when you get 10% interest. When you were doing this in the first section we covered, you would use 0.1. Okay, it's got to be in a decimal form. So the growth multiplier is 1.35. Okay, the growth multiplier or the common ratio. So this year's amount is equal to 1.35 times last year's amount. That's a pretty good growth multiplier, isn't it, Amanda?
Yes, sir.
I mean, Miranda. I'm sorry.
Yes, sir.
Excuse me.
Yeah.
I don't think I've ever made that kind of interest on anything. In fact, you'd be lucky to get 4% these days. Let's say, suppose you had a bad bank, folks, who charged you interest to put money in their bank. Okay, let's think about that, Stephen. And suppose I was going to charge you 2% each year. So you're not getting 2%. I'm going to get 2% for letting you put your money in my bank. Okay. So the rate is what? Minus 2%, right? So R is equal to what? Little r. Come on, folks.
Negative 0.02.
Yes. And so the multiplier, the growth multiplier, what do you think it would be, Jennifer? It's going to be 1 plus R, which is going to be what? What's 1 plus R if R is minus 0.02? Stephen?
Sorry, I had to walk away for a second. I missed all that.
Okay. Oh, did you hear about the new bank I'm talking about starting?
No, sir, I didn't hear that part. I had to walk away for a phone
Okay,
call.
I'm opening up a new bank and I'm inviting you to be one of my customers. And in this new bank, you pay me 2% each year instead of me paying you 2% on your money.
Okay, that sounds terrible.
Okay, you want to go? You want to go with me?
No, I don't think so.
I'll give you a coffee maker. Well, it's minus 2% each year is what the growth rate is instead of plus 2%, which you might be able to get on a bank account. So the R is minus 0.02. So what would the growth multiplier be? Miranda, you got an idea?
Be 0.98, wouldn't it?
0.98. So now, instead of multiplying last year's by 1.02, we would have piece of n, let piece of n be the value of what you got in the nth year. It's going to be 0.98 times last year. So you're losing 2% every year. So if you kept doing that and losing 2% every year, at some point you're going to be way, way down. Okay. Now, what do you think this could represent? You're not appreciating anything, are you? Your account's not growing. Does anybody have any ideas about why in the world you would have something model like this?
No, sir.
Okay. Okay, Jennifer. Suppose you went and bought a $100,000 car. Okay, you got the money for that?
No, sir.
You don't? Would you believe I don't either?
Mm-hmm.
But one of these, have you already bought a car, right?
No, sir.
You don't have a car.
No, sir.
I remember when I bought my first car after I graduated from Georgia Tech. Now back then, how much do you think a car would cost back in 1971?
A lot cheaper.
How about $4,000? I went down, I was really proud of getting my degree, and I had no money in the bank much. We were poor. Not poor, but I didn't have a lot of money saved. And so I took my diploma down to the Pontiac place and showed it to them. And they let me buy a car that I would pay them back. And the price was $4,000. How much do you think that car was worth 10 years later?
Probably like $1,000, maybe.
Yeah, one or two. It's called depreciation. Okay. And Jennifer, if you could buy a $100,000 car like a Rolls Royce, the next year it might lose 10%. Okay. So the next year, the $100,000 car might be worth 90% of that, which is $90,000. And the next year, it would be 90% of that, which would be 81,000. And the next year would be 90% of that. You see that, Jennifer?
Yes, sir.
Okay. So we've got, with exponential functions, we got exponential growth, and then we got exponential decay or decrease, okay, depending on whether the growth rate is positive or negative. But obviously, there are a lot of things we would like to see grow, like our bank accounts. A lot of things, though, when we buy them new, will actually go down in value. Do you know some things that would go up in value other than a bank account?
Populations,
Huh?
like the population.
Yes.
Um,
Yes. In fact, that's a good example, Miranda. The population might grow 5%. Well, it wouldn't grow that fast unless people were having a lot of babies. Okay. But I remember one of the first times I taught college algebra, and we got into exponential functions. And we looked at, back in 1776, the population of the US, I'd have to go back and look at it, was like 2 to 3 million. Now in the year 2019, how much do you think the population is? You could go Google it, couldn't you? How much do you think the population is? Now, I was teaching that course back in 2003.
You said for U.S. population, right?
Huh? The U.S. population.
Yes. 329 million.
Okay. That's what it is right now.
Correct.
In 2003, it had just hit 300 million. 300 million. And so there was a curve here of it going up pretty fast, and it was pretty close to being exponential. So population grows. What would you like to see go down? What would you like to see go down? Now, sometimes we talk about maybe not have as greater population growth as once we did. I remember when families would have 10 or 12 kids, but of course, the rate of death of kids back in 1700, 1800 was greater. So you just about needed to have more kids to keep it, have people to work on farms and do things. What would you like to see go down, though? Anybody got any ideas?
there's a lot of things I'd like to see go down.
What's that?
Unemployment, crime rates.
Yes, very good. You're right on unemployment. In fact, would you believe, I'm going to show you something on my computer. You mind?
That's fine.
You just made me think of something, because something I've been studying. That's not the one. I got two things called Bob Studies. Unemployment rates. You just mentioned it, Miranda. And so I went back all the way to 1950 and looked at the unemployment rate, which you can get. This is what the government publishes. And I also put in each president, all the way from Truman, Eisenhower, Kennedy, Johnson, Nixon, Ford, Jimmy Carter, Ronald Reagan, Bush, Clinton, Bush, Obama, and now President Trump. Okay. And what do you see? It going up and down in just about under every president. But notice back under Johnson, the unemployment rate was like 3%. Carter had some problems, and it finally got down to 5%. When the first Bush was in, he lost the election because the unemployment rate was getting bad. And so Clinton came in, and it went down to about 3 or 4%. The Bush 2 came in and it was higher. It went down. And then just as Bush left, remember we had a terrible economic situation at the beginning of Obama's, had a 10% unemployment rate. And as you're right, Miranda, we want that to go down. And so during his administration, it did go way down to about 4%. And one of the things that's happened recently, it has continued to stay down to about 3%. And so we hope it's not going to go back up anytime soon. But you're right. You just hit it. So I just took the chance to show you something I was interested in. Does that make sense, Miranda?
Yes, sir.
And this is right off the internet, but from the government. This is what every president quotes when they're talking about unemployment. This is called a civilian unemployment rate. Polio cases. Everybody's heard of polio?
Yes, sir.
Polio deaths had gone, or polio cases and deaths had gone up. Well, in 1950, when I was a kid, they were way up. And then the vaccine came in, and just about everywhere in the world, it's down to 0. But in several African countries, recently they had gone back up, and now they're going back down because Bill Gates. Everybody heard of Bill Gates, the Microsoft founder, has funded polio vaccines. So we like to see that go down. So I tell you what, one of the most important functions in the world is an exponential function because it describes a lot of things. Some things we like for them to go up, sometimes things we like to go down. And then we have the quadratic functions and the linear functions. Now, I'm going to close with a couple of things. Anybody ever seen this?
No, I haven't seen that.
This is obviously the year. You know, 1971 was about when I graduated from Georgia Tech and started working in electronics and working in satellites. And that was sort of the beginning of the computer age. And has anybody ever heard of a transistor?
Yes, sir.
Okay. Transistor replaced vacuum tubes back sometime in the 60s so that radios could be smaller, everything could be more compact. And they're very small compared to the vacuum tubes. And then they began to put transistors on a little chip. Has anybody ever looked at a chip in your computer? Well, there is a chip in your computer that has multiple transistors on it. And back in 1963, when I first had my first job as a freshman, there were 6 transistors on a chip. And then when I got to Bell Laboratories, it looked like there were about 1,000 to maybe 4,000 on a chip. Now look now in like the year 2019, what numbers do you see over here? What is that 5 and 10 followed by 9 zeros? What is that, 100,000, million, or what?
Billion.
A billion. So right now, on the very best computer, it's probably going to be about 30 billion. And folks, because of the exponential growth, that's why you have a cell phone that is so small. That's why you have a GPS in there that used to take up a whole room full of equipment. And it's called Moore's Law. The guy who started Intel began to realize that transistors on a chip were growing about doubling every year. And here's a diagram of a small chip that's got transistors on it. This is just a microscopic view of it. And the last thing I was going to mention to you folks is a great online graphing website. If you ever want to, you know, you can go buy a $100 calculator to do graphs. this is supposed to, well, let me find it. By the way, you type this into your computer and you could go and find this place. For some reason, it's not letting me click. Let me just go find the place. Online graphing tool. And this is absolutely amazing. It's free. I just put in y equal 2x squared and look what I got. Everybody see that?
Yes, sir.
I'm going to put in minus 3x squared plus 2x plus 3. And I can put any quadratic I want to. I can adjust the y values it will show on the x-axis and the y-axis. And you can graph anything. Now that's absolutely for free, folks. It didn't exist 4 or 5 years ago. So if when you're doing any of these calculations and using the formulas, if you wanted to graph something, you can do it right in front of your eyes. And it's a lot easier than using a TI-86 or 83 graphing calculator. So that's it. I sort of rambled along, so I apologize. Does anybody have any questions? Anybody have any questions?
Not that I can think of right now.
Okay. I don't know. I just had some experience with quadratics and exponential functions. I think it's astounding what is possible these days. The things that are increasing, the things that are decreasing. As you say, we'd like crime rate to go down, unemployment rate to go down. We'd like infant birth rates to go down in every country, etc. And hopefully, a lot of these things, if you get on them pretty quickly, they can go down exponentially. So anyway, that's that. I apologize for spending so much time, but I'm really excited about these kind of functions. They really mean something. Quadratics do. Linear functions, exponential functions mean something, and they're used all the time in our world. And those sine waves and cosine waves, which we're not going to cover, make your cell phone possible. So anyway, does anybody have any comments? Okay, well, I'm going to end the meeting now, and I'll put this up. You guys take it easy.
Thank you.